Welcome to this explainer. We're diving deep into the hidden cost of doing everything right now and how to permanently change the way you design backend features. We're looking at exactly why systems collapse under load, and I'm going to show you the exact architectural patterns that the highest scale engineering teams use to fix it.
We've got a lot of fascinating ground to cover today. We'll start with the synchronous death trap, move into the delegation blueprint, compare queues versus streams, demystify Kafka's architecture, run through a production survival guide, and then wrap it all up with the golden rule. Let's get to it.
All right, part 1, the synchronous death trap. We're starting right in the trenches here with a problem literally every backend engineer faces as their application's traffic begins to grow.
So think about this. What actually happens when your API has to do, say, 15 things at once? Imagine a user clicks publish on a blog post. In a perfect, simple world, you just save it to the database and return a quick success message, right? But in reality, before your API can even think about returning that 200 OK, it suddenly has to juggle this massive list of background tasks.
Think about all these synchronous side effects. You've got to persist the blog to the primary database, increment a total blogs counter, index the text into Elasticsearch, generate image thumbnails, fire off notifications, and update analytics. If you couple all these side effects to the user's requests synchronously, your latency basically becomes the sum of every downstream system's worst day. Seriously. A slow search index doesn't just make searching slow, it literally breaks the entire publishing feature. You're creating this massive blast radius if absolutely anything fails.
So how do we fix it? That brings us to part 2, the delegation blueprint. To convert those catastrophic failures into gracefully degraded experiences, we need a complete architectural pivot. We have to stop trying to do everything on the user's time.
What does not need to be done in real time should not be done in real time. Honestly, if you take one thing away from this explainer, make it this mantra. Internalize it. Your user only cares that their blog was saved and that the API felt snappy. Everything else, the analytics, notifications, search indexing, that can all happen eventually. And you know, that word, eventually, is the absolute key to horizontal scalability. To actually delegate this work safely, we use the transactional outbox pattern. Why? Well, if you just write to your database and then try to fire a message over the network to a broker, you create what's called a dual write problem. If the network blips for even a second, the database has the blog, but the search index never gets the memo. It's a nightmare. So, by writing the blog data and an event to an outbox table in a single atomic database transaction, we guarantee that those side effects are an absolute unavoidable consequence of the database rate. Once that event is generated, it gets sent over to a broker. The best way to think about a broker is like the shock absorber on a car. It absorbs those massive, unpredictable traffic bursts, so your backend workers can drain the backlog at their own pace. If your API suddenly takes 50,000 requests per second, but your workers can only handle 5,000, the broker simply holds the difference. Without it, your system would buckle, and those user requests would just flat out fail. Moving right along to part 3, queues versus streams. Now we hit the industry's biggest point of confusion, and getting this right basically dictates the rest of your system design. Understanding the difference here is non-negotiable. Queues, like SQS or RabbitMQ, are for parallelizing identical tasks. Think of it like a restaurant pickup line. One order goes to exactly one worker, they process it, and poof, it's deleted. Streams, on the other hand, like Kafka or Kinesis, are entirely different beasts. They are an append-only log. It's much more like a river. Different consumer groups can sit on the riverbank and catch the exact same fish or, read the exact same event, completely independently of one another, and the stream retains that history. And this leads us to the heterogeneous consumer pattern. Having a single worker handle analytics and search indexing is a huge anti-pattern. It completely violates the separation of concerns. If the search team deploys a bad bug, why should the analytics pipeline crash? It shouldn't. Streams allow different teams to consume the exact same blog-published event entirely independently. Let's transition to part 4, Kafka architecture demystified. We're going to pull back the curtain on Kafka, starting with the core primitives you absolutely must understand viscerally to use streams effectively in your architecture. Okay, so a topic is simply your named stream, like blog.published. But the real magic? That happens in partitions. A partition is your unit of parallelism. When you publish an event, Kafka uses a partition key, something like a user ID, to decide exactly where it goes. Messages with the same key always land in the same partition. That is exactly how you preserve strict ordering for related events. Then, the offset is just a marker that tracks where a specific consumer group is on that particular partition. Now listen to this because it is absolute gospel. A partition can only be consumed by exactly one consumer in a group at a time. Period. If you have 3 partitions but you spin up 5 consumers in a group, 2 of those consumers are just going to sit there completely idle, doing absolutely nothing. This means your partition count is your absolute maximum scaling ceiling. And here is the catch that bites so many engineers. You can increase partitions, but you absolutely cannot decrease them. Why? Because reducing partitions requires reshuffling messages by key across the entire cluster, which immediately breaks all your strict ordering and offset tracking. So you have to plan your partition counts conservatively, usually starting around maybe 12 to 24 for a standard service, but you always have to keep future growth in the back of your mind. All right, moving into part 5, the production survival guide. Theory's great and all, but in reality, systems crash. Let's talk about actually surviving production, specifically looking at some idiomatic patterns you'd use in a language like Go. When building producers and consumers, autocommit is incredibly dangerous. It can mark messages as processed before they actually are, which causes silent data loss when a crash happens. You need manual commits. For your Go producers, make sure you require all acts from all replicates to prevent data loss. On the flip side, idempotency must be enforced at the consumer level using unique event IDs. In distributed systems, network partitions and duplicate deliveries aren't just possibilities, they are inevitabilities.
Anticipating these failure modes is really what separates senior engineers from the rest. Take the poison message scenario, for example. A single malformed payload from a producer can crash your consumer worker. If that worker restarts and tries to process the exact same message again, boom, you are stuck in an endless loop. Routing those bad schemas to a dead letter queue, or a DLQ, instead of blocking the entire partition, is absolutely critical to keeping the rest of your traffic flowing smoothly.
Of course, literally none of this matters if you can't see what's happening under the hood. If you aren't monitoring consumer lag per partition, you are flying completely blind. Consumer lag is the most critical signal. It tells you if your workers are falling behind the influx of messages. Without it, you won't even know your system is failing until angry users start reporting that their blogs aren't showing up in search, and nobody wants that. Finally, part 6, the golden rule. As we wrap up this explainer, I really want to pull all of these technical details back into a single cohesive philosophy for you to take back to your engineering teams. Here is the ultimate takeaway. The hardest part of scaling a backend isn't writing hyper-optimized, incredibly fast code. It's deciding what doesn't need to happen right now. When you fully embrace delegation, brokers, and eventual consistency, your architecture practically writes itself. You start converting what used to be catastrophic crashes into minor background delays that your users might not even notice. So, I want to leave you with this provocative thought. Look at your current API bottlenecks right now. Which of those massive synchronous operations can you delegate to a broker today? Just think about the immediate relief your systems will feel when you decouple those side effects. Dive into Kafka, set up an outbox table, and start building true resilience. Thank you so much for joining me for this explainer, and happy building.